All right, so yeah, what's possible in observability when we have frame pointers is kind of the talk. But let's start out with like a kind of like actual use case of observability, right? So we have these workloads, we can like graph the CPU cores, and we can see some things happening, and we might be wondering what's actually happening at these spikes, right? And we can use profiling, I guess, to figure out what happens at these individual spikes, just to like understand, okay, like in this scenario, this was happening in another scenario, or like at another time something else happened. We can like get profiles manually and compare them, or we do something called continuous profiling, where we just like all the time, over time, profile. Hopefully, little overhead. We can even do it in production, or not hopefully, but it's a reality. We can do it in production, right? So we can then store all of these profiles, and over time, kind of like ask questions when we want to in retrospect, and we don't have to worry about missing data points, and we have kind of the security or the ease of use that we can just click on some spike and then get a flame graph, or in this case an icicle graph, because it's like top down and not the other way around. We call it icicle graphs. And you can see all the stack traces, and you can like instrument very nicely, introspect what's happening. And I don't have a slide for this, but we can also kind of like diff flame graphs, and then we can see in like red where things got worse, in green usually where things gotten better. And it's pretty obvious most of the time if you have such a big spike, like that's right the point where we need to look in such a flame graph, and where we need to like check out what's happening in the code. So yeah, that's kind of a pretty good use case for observability, right? But yeah, what are frame pointers? But before we come to that, quick introduction. I'm Matthias Leube. I'm a senior software engineer at Polar Signals. I work on Parka, which is like the open source project doing a bunch of these things, but I also work on Thanos, Prometheus, and lots of other open source monitoring projects.
Yeah, and hey everyone, I'm John Seeger. I'm VP of Engineering at Canonical. I have a kind of interesting journey to open source, but at the moment I am leading the development of Juju and a whole suite of kind of enterprise apps, which we call charms. So if you want to get access to like the best Postgres on your infrastructure, or the best MySQL, or the Grafana stack, or Parka, or you want to build an identity stack with Ori and with OpenFGA and products like that, that's kind of the effort that I'm leading. The orchestrator is called Juju. It's been around a really long time. Charms are all written in Python, and we're kind of building out a big catalog of operators that allow you to not just deploy those things, but actually compose them all together and integrate them in a really common way, irrespective of whether your infrastructure happens to be bare metal, or Kubernetes, or VMs, or on EC2, or on Azure, or some combination of the whole lot. So that's kind of what I'm up to at the moment.
Awesome, yeah. And I'm looking forward to hearing more from you. But before I do that, let's talk about profiling again, or like what profiling data is made up of. And you can see these like points in time, just T1, T2, T3. At some point in time, we basically want to look at the current stack trace, what the program state looks like. And we can see that like at T1 we had A, B, C, D. At T2 we had A, B, C, and E, so slightly different, and then at T3 we had the same thing again. So kind of like just for the sake of the demo or the example, one was like executed twice, so maybe it was like executed 20 milliseconds in total, and the other one 10 milliseconds, right? So we kind of like count how often we see these stacks, and then kind of can make assumption on how much it is running. And this is kind of like a sampled profiling profiler. It basically only like every so often looks at these stack traces, but over time we can really nicely like see the big picture of things happening, right? The good thing is, because it's only happening so often, the overhead is pretty low, which again I touched on earlier for our use case, figuring out what's going on. It's pretty nice due to being pretty low overhead. So how do we get to these stack traces, right? Like how can we see these stacks that we then get all the memory addresses for, and then we can like nicely format them using the function names, for example, in the icicle graphs. So the best case, and that's kind of the whole point of the talk, right, are frame pointers. And frame pointers, looking at this bit of C code, it's hopefully not too daunting in a monitoring and observability room, but we can see we have the main function at the bottom, and that calls a function, and so on. The functions call each other, and then at the very top, it just goes into an endless loop. And kind of the important part in all of this is looking at the assembly on the right-hand side. We can see that, okay, I omitted like the main function and the A1, but then we can see B1, and we can see that at the very beginning, we are pushing and moving some registers around, and those are actually the instructions to push the frame pointer onto the stack. And then we are calling the next function, right? And the pushing of the registers is so that we know once the next function is done executing, we can come back to exactly that previous function and continue executing. The one thing I want to mention here is in the past there were a couple of discussions about the overhead of using frame pointers. So we have the push and move instructions, and then once the function is done, it needs to pop that frame pointer. So there were a couple of extra assembly steps involved. Especially on 30-bit systems, it wasn't great performance-wise, but I think unless you're a really, really special case, it should be fine for almost all workloads, even in production. And that's kind of the point of this. So basically, our binary on the left-hand side, we can see our setup frame pointer. So that's kind of the first instruction that our assembly is executing. It is putting the frame pointer onto the stack before then going and doing the actual call to the next function, right? And before doing that, we have to add the return address to our stack so that once the function that we're calling is done, we know where to continue in our current function, right? So we need to know where, like this other code we need to execute after calling the function we are calling right now, where we need to continue. So that's why we have the return address. And we then actually do the function preamble, and we run that function, and eventually we return the function. We are at the pointer that then actually tells us where to go back to, right? So the function that we called eventually returns, and we want to go back to the original function. However, we are then executing after that function call, right? So previously we were, I don't know, can you see my mouse? No. We were over here, and now we returned like one step after that, right? Because we don't want to call that function again, going into an endless loop. We want to continue afterwards. However, we want to know what called us, right? So basically, what we want to do is whenever we have a stack, we want to know which function called us, and do that all the way such that we eventually end up in the main function, and we know all the functions that we have on the stack up to the point where we are now. So basically, that's kind of like walking the stack here. And the really, really cool thing is we can do this in eBPF. So I don't know how many attended the previous talk. eBPF, kind of a hot topic right now. For us, it's really, really cool because what we can do is write a small program in a C dialect, and then get that through the verifier and compile it into eBPF code, and then load that into the Linux kernel. And the way it works is then we actually don't use syscalls like the slide originally says, but what we then do is like tell the Linux kernel to every so often run this snippet of eBPF code. And what we do is do this like stack unwinding or stack walking that I told you about like 2 slides ago. So essentially what we do is we start in eBPF, we get kind of the context, we get the current stack pointer, and we look at the leaf of the stack, so like kind of the very top, like the currently executing function, and we can then use that to essentially read that instruction pointer, and from there get the frame pointer. And the special occasion here is the instruction pointer has to be the return address -1 because of the thing I just told you about 2 slides ago, right? So basically that's how we can then know where we were called from. And we do that all the time up until at the end we get an instruction pointer, or that's 0. So this one then means basically we reach the end of the stack, and we know we can terminate, or we reach the end of that stack trace. In between, for profiling, you can see over here we do something with the stack, with the frame, and what we actually do is we kind of like just get the memory address of that executed function, and we basically have an array of all the frames that were executed at the end, and have the memory addresses, and those memory addresses we can then use to get the function names for that function. So having frame pointers in eBPF makes regular profiling super easy, and we can then do profiling super simple. We don't have to worry about like special compiler configurations, because we can just assume that frame pointers are here for us to then basically use them to figure out the entire stack of the currently executing function. There are ways to do exactly that without frame pointers, and shout out, I think it was in this very room 1 year ago, there was a talk by Javier and by Charlie, who were talking about stack unwinding without frame pointers using Dwarf. I highly recommend it. It's really, really interesting, but something for another time. And then obviously, not only like the profiling use case, but if we have frame pointers in the executables, in those executing stacks, we can also use all the other debugging tools, right? Not only for profiling, we can use the bcc-tools, bpftrace, perf, etc., and they also have the kind of same benefits. So essentially, what that means is that the possibilities really become a lot more broad and open, or like we can do a lot more things because we only have these like 2 memory reads. And for example, in bpftrace, we can use the like one-liner here to essentially also build a really simple but working profiler that uses the uStack to get the user space stack unwinded and count how often it sees things. And that's super cheap then. But also like the Go execution tracer actually traces everything that's happening, and because unwinding is has so little overhead, we can also do things like that. And once we have profiles, continuing kind of like the performance aspect, we can do something called profile guided optimizations, and just making profiling so cheap, that's something where I think a lot of innovation is also going to happen in the future. And some outlook, like some super new paper, is the context-sensitive, sample-based profile-guided optimization. So something we are super excited about, because it will allow a lot more things to happen as well. But maybe another FOSDEM talk is going to happen about that in a year or two. So bringing frame pointer to the masses, I'm super excited to have John talk.
Hey, all right, so I'm here to tell you about, now we've seen all of the cool stuff you can do when you have frame pointers, how we at Canonical are going to make this available to all of you much more easily. And so if you didn't see this announced on our blog a couple of months ago, we have decided that from 2404 LTS, we're going to enable frame pointers for the entire Ubuntu archive on 64-bit platforms. The caveat on 64-bit is because back in the day, 32-bit CPUs obviously had far fewer registers, and so sacrificing a register to hold the frame pointer came with a much higher performance overhead. In reality, these days with 64-bit, you're looking at, on average, kind of less than 1%, unless you're in a very specific group. So if you're doing like turbo pants-on-head HPC stuff, or high-frequency trading, or real-time things where kind of that like 1% could really, really matter, perhaps this isn't for you, and we can make exceptions in the archive for those packages. But in general, for 2404, you can expect to see frame pointers for the entire archive through main and universe, etc. This is pretty exciting, because the LTS, I probably don't need to tell you, is going to be installed on many, many millions of machines, right? And then supported for at least 10 years by Canonical. So this is going to make a big impact for people who need these things. This stuff is often already enabled by the hyperscalers, so people like Amazon, people like Netflix, people like Microsoft are already doing this in production, and now you kind of get it for free as well just by using Ubuntu. So I mentioned there will be some, pretty much negligible, barely noticeable for nearly all use case performance impact. we're kind of willing to wear that because what it actually enables in the medium term is for us to do a lot of work on our distribution, right? So we're in the process now of running benchmarks on a kind of pre-frame pointer Ubuntu and a post-frame pointer Ubuntu ready for the release, and that will hopefully help us identify any outliers. So if we hit certain packages where we feel like the performance hit is too much, then we will disable it for the first release of 2404, or we will try and work out what other optimizations we might make to that package to make it work better with the frame pointers enabled. So this will really, really help, I think, downstreams to enable, or to gain the benefit of frame pointers and optimize their own workload. So if you are someone who just uses Ubuntu as a platform and you build your own code, and let's say you use Python, or you use Go, or you use Node.js or whatever, suddenly those big holes in your frame graphs are just going to disappear when you move to 2404 without you having to do anything. This is really just the start. We're trying to make 2404 a really focused release on kind of performance engineering and performance itself. So what does that actually mean? Having the frame pointers is one thing, but you also need the tooling to actually utilize the frame pointers and kind of inspect the stack. The folks at Polar Signals with Parquet are one part of that, but we're also looking to include tools like bpftrace and sysstat and the perf tools unstable by default in Ubuntu. Not in every single image, so those of you that are about to scream at me because you use the minimal image or you ship 100,000 container images a month and you don't want to ship bpftrace in all of them, don't panic. We are essentially going to enable all of these tools by default anywhere where we ship a kernel, right? So a Ubuntu server image, a full-size server image, that doesn't include LXD images, it doesn't include OCI images, but if you install Ubuntu on a server or in a VM, you will have bpftrace by default, you'll have sysstat by default. Essentially, a huge majority of the tools that Brendan Gregg describes as crisis tools will be there by default. And the reason that's super important is because if your system is in crisis, it doesn't matter whether the tools are in the archive, right? If your system is right on the edge, and then you hit the system with a whole bunch of network I/O and disk I/O to go and get a package from the archives, it's potentially going to put that system over the edge. It may not even work in production, right? Like the system may not have access to the package archives, and so you just need those tools to be there, and we're going to make sure that happens. For places where we don't ship a kernel, all of these tools will get wrapped up in a new meta package. So if you do want it in your LXD containers, if you do want it in your container images, in your debug images, then you'll just be able to see it really, really easily with a single meta package. We're looking at what other compiler optimizations we can make across the archive as well. So this might look like rolling out GCC03 for a huge part of the archive. We're not going to do that in kind of one big bang go because there are some trade-offs there. And we're also looking at essentially not maintaining a low latency kernel and a generic kernel and just shipping the low latency packages by default. None of these are like firm, 100% definitely going to happen in 2404. These are the goals we're working towards before the release in April. And finally, some of you may have seen we've been doing some work on working out how to get Ubuntu and the archive to take advantage of the kind of newer instruction sets, right? So AMD 64 v3, AMD 64 v4, v5. We actually have a build of the entire archive that uses AMD 64 v3. You can get it in a PPA and test it and benchmark it. It's faster, like TLDR, but we need to do a bunch of upstream work in apt to work out how we can essentially kind of multiplex that, right? So that you still just go ubuntu.com/download, download an AMD 64 ISO, and it does the right thing without you having a massive long list of different instruction sets to choose from for AMD 64. So that work is coming, but probably won't land for 2404. We also continue to introduce new patches into things like GNOME. We're still trying to get the GNOME triple buffering stuff landed, ready for 2404, which gives a kind of much smoother experience on the desktop as well. So this runs really from Ubuntu server right up through to Ubuntu desktop. And these tools will be available to desktop users too. So you as a developer on Ubuntu should have access to the same debugging tools that you find in your production workloads, in our opinion. On a side note, we are trying to do this at a really big scale at Canonical. We are hiring practice leads that will sit in a central team to build processes and tools and essentially give advice across our 40 or so products. And we're also hiring dedicated performance engineers for every single team, whether that team be doing Go, Python, Node.js, C, or whatever. So if you're interested in that, talk to me afterwards. Check out canonical.com/careers. There's a couple of Canonical folk in here as well who you can talk to. If performance is your thing and you want to come and make use of frame pointers and make Ubuntu blazing fast, then that's always an option to you. And finally, from my side, we've done a bit of work with Polar Signals. They kind of have been helping us along this way. We've got snap packages and charms available for Parquet, both for the agent and the server. So on any Ubuntu machine, you can seed this in a cloud init file with a single line. You can snap install the Parquet agent, give it a single config with a token, and start continuous profiling out into Polar Signals cloud. Or you can host the server infrastructure yourself on machines, on Kubernetes, on containers, whatever it is with Juju. And we'll continue to kind of make improvements to that over time. So it's a super, super easy way to get hold of this nice continuous profiling hotness in Ubuntu. And that's it. Get in touch.
So thank you very much for that. Looking forward to the Ubuntu release. Are there any questions? Questions, anyone? Once, twice, nobody? Okay, then thanks again. And next up we have Quickwit, I think, in 20 minutes.
Thank you. Bye. Cheers.